Hello and welcome back. To rewind, we were discussing particle image velocimetry. I had shown you this particular diagram and I had told you that there are these different aspects of particle image velocimetry which depends on a case to case basis on how you will choose the right optical elements, the right light source, the right tracer particles, etc., and the right camera also. And even how the process of imaging and the image processing also. So, we will go one by one through all these different aspects of particle image velocimetry. Last time we also already talked about tracer particles. We have understood how theoretically tracer particles need to be chosen, what are the theoretical considerations, and then we looked also at the practical considerations. So, we talked about some of the realistic choices that are there. Those choices are indicative and not the only choice. So, you should be careful, and when you are doing your own experiment you have to make a choice based on your particular experiments and the particular conditions that are prevailing there. So, having discussed that, next topic I would like to discuss is the topic of the light source, and then I will discuss the topic of the optical elements. Now, in the optical elements case, there are actually a number of different possibilities, each depending upon the particular case. But what I will restrict myself to is the conventional particle image velocimetry setup where cylindrical lenses are used to create light sheets. So, we will look at some of those calculations because that is very traditional and a very often used situation. Okay. So, let us go back to our writing pad and we talk about the light source. Okay. So, we have talked about the tracer and now we are going to talk about the light source. Now, lasers are very widely used in PIV. There is a good number of reasons for that, and the reasons are especially due to their ability. I hope the first thing that comes into your mind is the monochromaticity of lasers. So, emit monochromatic highly collimated light with high energy density. And because of this nature, lasers can also be easily sculpted into thin sheets for illuminating and recording tracers with minimal chromatic aberrations. Chromatic. Now, example again, for example, a very often used laser is the helium neon laser, which is usually operates at 633 nanometers. We also have argon ion lasers, which are often used. Here the wavelength is either 514 or 488 nanometers. Semiconductor lasers are also quite popular. Such as ND-YAG and ND-YLF. Lasers are also quite popular. This, for example, comes usually in two different wavelengths, 1053 and 526. The natural wavelength is the higher one, and then you can do a frequency doubling and end up with 526 nanometer wavelength also. Now lasers are not necessary, okay, they are not a necessary precondition. Lasers, as I said, they are widely used because of their high energy density, and by which I mean, what practical consideration behind that is, if you take an image with a very low exposure time, laser will give you enough light in order to be able to record good signals. Whereas if you have a white light source, it might not have a high energy density, so if you start taking very low exposure images, then you may not have good image quality. So that's where the difference is, but white light sources can also be used. There's nothing against it as such. It again depends on a situational, it's very situational. So I am going to mark this that white light sources may also be used, and they cannot be easily collimated. Easily collimated, and usually have low energy density. However, for slow flows, for very slow flows, white light sources can suffice. Okay. Xenon lamps are an example. Xenon lamps or LED lights are examples. LEDs, though, they can come in specific colors, so then it's not exactly a white light source. Sometimes to have a white light source, different LEDs are put together. But even otherwise, if you are using a colored LED, you will get a set of specific wavelengths. So now to decide all this, you have to look at the type, sensitivity of the sensor, and exposure time are important determinants of the type of light source. Okay. So again, we are not giving you absolute principles here. We are just indicating to you what are the typical cases. Now, if we go back to this particular image that we had seen, you see there is a cylindrical lens that is being used, and the beam of light that is coming and is becoming a sheet right here, right. So you can see the laser sheet approximately in this location. So for that we have to use cylindrical lenses to create laser sheets. So with regards to the optical elements, I am not going to discuss in detail all possible optical elements because that will be too exhaustive for this course, but we are going to discuss this particular issue of light sheet optics. Now I will ask you to look up simple geometric optics if you are not familiar with it. But in simple geometric optics, we discuss how lenses form images. Lenses can be thick lenses, they can be thin lenses. For thin lenses, there is a very famous equation that relates the image distance, the object distance, and the focal length of the lens. So for example, if you have an image, an object here which is forming an image somewhere, and let us say this distance is S naught, and this is, let us say, S I. Then this famous equation is valid for thin lenses, which is 1 by S naught and 1 by S I is equal to 1 by F. F is the focal length of the lens. And here the sign convention is important. I am going to adopt a sign convention of a particular book. Different books can have different sign conventions. So you are free to pick from the right one. If you choose a different sign convention, you will just have to worry about the proper equation, the pluses and the minuses. So just be careful with it. So in this particular sign convention, we say something is positive. So let's say we have these three quantities here, S naught, Si and F. S naught being the object distance, Si is the image distance, and F is the focal length of the lens. And if you have a real object, we associate a positive sign with it. If you have a virtual object, we associate a negative sign with it. Similarly for Si, it's positive, it's a real image, and it's a virtual image, it's negative. And F is positive, it's a converging lens, and F is negative, it's a diverging lens. Now, if you wish to refer to a book, I will give you a particular reference, and you can look up other reference texts too. But this is a book that I used, so I'll just give you the name of the book. This is called Optics, and the author is Eugene Hecht. And this is I believe the copy I have is by Pearson Education, and you might have you should look up the current publisher of this book. So this is a book you can refer to, or you can find any other book. As I said, different books have different sign conventions for discussing geometric optics. So you should just be careful. If you use a different book, make sure that you know the proper sign convention that they are using. Now, the important thing to discuss here is a two lens combination. Obviously, there are multiple lens combinations, so you can go on by creating a more complicated setup by just putting lenses together. Obviously, the simplest complex system in this case is a two lens system. So we will discuss what happens if you have two lenses. So let's say you have two lenses which are separated by a distance d. And let's say the focal length of the first one is given by f1, focal length of the second lens is given by f2, and let's say you have an object, and the distance of the object from the first lens is S01, and this object finally forms an image somewhere in the system. So, and we'll call this particular distance from the second lens some Si2. In such a case, geometric optics, and I am stating the result without any proof, and again you are free to look up the book. This Si2 is given by this equation, F2d minus F2 S0 so 1 F1 divided by S1 minus 1 divided by d minus F2 minus S. So this above equation, it tells you how an object of a finite size located at SO1 will be imaged in the optical system and where this image will be produced. So this allows you to calculate that. Now, what is interesting in light sheet optics is that the first lens is usually a converging lens, whereas the second lens is a cylindrical lens. Okay. So that is what makes things interesting. So we'll look at it. And in light sheet optics, the light that enters from the left is usually a collimated beam, laser beam, right? So in light sheet optics, we are concerned with a collimated beam of light, which is a laser, and which passes through the system, collimated beam which passes through the system. So my SO1 is basically infinity. So and wherever this wherever the image forms when a collimated light enters, that distance you can calculate now with this above formula, and that distance is also called the back focal plane. Okay. So the back focal plane is where the image is formed when you have a collimated light entry. So I can say in mathematical terms that my SI2 and the limit of S01 becoming infinity is also called the back focal plane. And this distance, if you simplify using the above equation, this simplifies down to this equation now. I urge you to verify this by yourself and make sure that I am using it correctly. Now if the lens is very thin, sorry, if the lenses are really close, okay, sorry, I am not the thin, these are already thin lenses. If the lenses are really close, which implies that is d tends to 0, then my back focal plane equation becomes even simpler and reduces to f2 f1 by f1 plus f2. So armed with this, the best way to understand light sheet optics is through a sample calculation. So let's say you have I'm going to draw two. I'm going to draw first the side view of this and then the top view, sorry, top view. So let's say we have a spherical lens with a cylinder coupled with a cylindrical lens. So we have a spherical lens which in the top and the side view looks the same, and then on this side you have a cylindrical lens. So in one of the views the cylindrical nature is can be seen, and in the other one all you have is a rectangular slab, so it does not do anything to the light. And let us say that this distance is given to us. So d is given to us as 10 mm. The first lens is a spherical lens, the second lens is a cylindrical lens, and the focal lengths are provided to you. So your first focal length is 500 millimeter, I'm sorry, and the second lens f2 is minus 25 mm. Now you see the advantage of having set up the proper signs convention here. We have already set up the sign convention, so we know what a negative sign for an f means, right. But interestingly, in the second case here, the top view, the effective focal length is 0, right. So you have to be careful in interpreting the number. Now both the side and the top views, I want to reiterate, they show you the same setup, physical setup along two different axes, and because of the cylindrical lens, the image that I've, or the figure I've drawn and the two for the cylindrical lens, they are different. Okay, so now we can do our calculation, and so the whole idea is that there is I'll need a different color to say. Okay, let's see. So we have, let's say, a light coming in, a collimated light which comes in. This collimated light goes into my cylindrical lens. As a result of the cylindrical lens, this light diverges like this in one of the axes. Whereas in the other one, the light in the other axis, the light only sees the spherical lens and basically just ends up converging somewhere on this point. So this is maybe the location of the back focal plane. So if you had to do a quick calculation about the back focal planes, etc., I encourage you to try and do this yourself right now, because we have given you the equations. So I'll give you a minute to think about the particular problem, and the question that we are going to ask you is give us the geometrical parameters of this light sheet. So I'm just going to stop for a second here and let you do the calculation and pick up right after that.